Today we will start looking at what is called two-body problem. Okay, here you have two particles of masses m1 and m2 which are interacting with each other and there are no external forces present. Okay, so that's the situation. So you have a particle of mass m1, another particle of mass m2. Okay, and let's say this guy is located at R1 and this particle is located at R2 with respect to some origin, which let's say it's here, which means this is R1 and this is R2. Okay, and these two particles are interacting with each other, and let's say the potential energy due to that interaction is U of R1 R2. Okay, so the interaction is given by the potential energy R1 R2. It's a function of R1 and R2, and there are no external forces on this system. So this is what is a two-body problem. So you have two particles, two bodies, and they are interacting in a certain way. So here I have made an assumption that the potential energy only depends on where the particles are. Okay, that's the assumption I have made. But now I want to further assume, which is very reasonable, further assumptions. Okay. So I assume that the force is such that the potential energy does not change if you take the entire system and move it to somewhere else. Okay, meaning it cares only about what is the difference between R2 and R1. Okay, so if I translate this entire thing by some amount, the potential energy does not change. So I am saying that U of R1 R2, okay, is same as U of R. Let me put the first one here, and this does not matter. So here what I'm saying is it cares only about the vector which is separating them. Okay, the difference vector R2 minus R1. Okay, that's nice, and this of course is not unreasonable. This is a very reasonable assumption because that's how most of the things will behave. If, for example, you think of two particles which are interacting gravitationally, if you take the entire system and shift it to another place, millions of kilometers away or billions of kilometers away, the potential energy between those two will not change. Okay. Now, not only that, we want to further assume that U of R1 R2 is only dependent on the distance between these two particles. Okay, so this is clearly different from this. Here it still depended on the direction in which R2 minus R1 will point, right? So here let's say this is R2, this is R1, so this vector, this is R2 minus R1. So when I write here this way, it means that the potential energy cares about in which direction this vector is pointing. So if you rotate this, for example, this entire setup, then the R2 minus R1 will be pointing in some other direction, and it says that okay, it may depend on it, And here I am going to be more specific and saying that even if you rotate this so that the direction of r2 minus r1 changes, it still does not change if the separation distance is fixed. Okay, that is what is meant by this expression, which is also not unreasonable. This is a very reasonable choice because you know that space is homogeneous and isotropic. So if my system is not being affected by any other external agents, then space will be homogeneous and isotropic, and translating as a whole the entire thing, or even rotating the entire setup, should not change how the system is going to behave, which means that the potential energies should be given by such restricted form. Okay, let's see. Yeah. Now, if this is the case, then we say that the force is central. Okay, central force, which means just that your potential energy depends only on the separation between the two particles of your system. That's a central force field. Okay, now let's ask, we would like to solve this system, and this system is solvable. We will see that we'll be able to find the full solution to this. But at the moment, the goal is to figure out as much we can about the system without specifying anything about the potential other than what we have already said. Okay, so I do not want to assume any special form for the potential, that it falls off this way or that way, and I want to see how much I can say about such a system just based on the fact that this is a central force system. Okay, so one thing is clear, that this is a 6-dimensional system. This has a 6 degrees of freedom, which is obvious. Each particle has 3 degrees of freedom. So the system is a system of 6 degrees of freedom. And let me try to create a separation. Yes. Okay. Okay, fine. So what's the Lagrangian of this system? It's easy to write. It's just the kinetic energy minus the potential energy, and we have already written down the form of potential energy. So your L, the Lagrangian, is half m1 r1 dot square plus half m2 r2 dot square minus the potential energy, which is r2 minus r1, the modulus of it. Okay, it cares only about the length. Now we ask whether these are the best coordinates to describe the system. Now, our experience with several different systems before may immediately tell us that these are not the best coordinates. It would be wise to use r2 minus r1, the modulus of it, as one of the coordinates, and the other coordinate which will be good to use will be the center of mass coordinate. Okay, we have come across this thing several times, so I will not go further into this and just write down the transformation. Okay, so what we want to do is we want to do a transformation of coordinates from R1, which is, I will call x1, y1 and z1, and R2, which is x2, y2 and z2, and from this I want to go to R, capital R, by which I denote the center of mass, m1 r1 plus m2 r2 over the total mass of this system, which is m1 plus m2, and small r, which is r2 minus r1. So I go from these 6, 1, 2, 3, 4, 5, 6 to these 6, because r is of 3 vectors, so it has 3 components, and small r is also 3 vector, it has 3 components. So I've gone from 6 to 6, and let's see why this will be very useful. But before we do that, let's invert this and write down R1 and R2 in terms of capital R and small r. Okay, so please do this exercise. NVERT, correct. So please check that what I'm writing is correct. R1 you can write as the center of mass, location of the center of mass minus m2 over m1 plus m2, and this small vector r, which is the separation vector, and then your r2 is this plus m1 over m1 plus m2 times r. Okay, that's nice, and this will be very useful, because when I try to find out what the kinetic energy is, which is here, this in this place, and when I substitute these R1 and R2 in there, I find a very nice result, which is kind of expected. So please do the following exercise and check. Okay, I had a plan of using green when I'm giving exercises. Okay, so please check that the kinetic energy T becomes half m kinetic energy, which is half m1 r1 dot square plus half m2 r2 dot square, becomes half m1 plus m2 r dot square, which is the coordinate of the center of mass, so the velocity of center of mass square, plus half m1 m2 over m1 plus m2 r dot square. Okay, let me check the dimensions. So I have 2 powers of mass here, 1 power of mass below, so it makes 1 power, which is consistent with this one, so it looks fine. Okay, good. Now let me define by capital M, m1 plus m2, the total mass, and I also introduce mu to be the following. Okay, so that's the definition of mu, and you can see that this piece here, m1 m2 over m1 plus m2, is just mu. Okay, and mu is called the reduced mass. So with this, what is our Lagrangian now? Our Lagrangian looks like the following. So my Lagrangian is now half m r dot square. Then you have the reduced mass term, which is half mu r dot square, and then we had the potential term, which is u of r, okay, where I have introduced new notation, which is r2 minus r1. So this vector, this r without any vector symbol, is this quantity. Okay, that is good, and it's nice because you see the coordinate capital R, the center of mass coordinate, that is a cyclic coordinate, which is what you expected. Okay, this is nice because now I can immediately solve the equation of motion for capital R, and I know what I will get. I mean, you can do it, but that's what you're going to get. The equation of motion for R is r dot is equal to constant, which just says that the center of mass moves with a constant velocity. That is what is expected. And then we can drop it from the Lagrangian, because the equations of motion of other coordinate r is not going to be affected by what is happening to capital R. So I can take my Lagrangian to be half mu r dot square minus u of r. Okay, now you see this is very nice because this looks like, I mean, not like, it is exactly of the same form as of a particle of mass mu, which is moving in a potential field which is given by u of r. Okay, central potential field. So this Lagrangian is same as the Lagrangian of of a particle of mass mu moving in a force field u of r. So you understand what is happening. You started with a system which had two particles, but with a good choice of coordinates, the system appears to be equivalent to another system, which is a very simple system where you have a particle of mass mu which is moving in a center force field which is given by u of r. Okay, that is what it looks like. So if you can solve this system, this new one to which we have reduced our original system, if we can solve it, I can invert back. So let's say I solve for small r and I have capital R. From that I can construct my R1 and R2, and I will know about my original problem, right? So that is what will provide us the full solution to this problem. Okay, so we will now proceed from here and ask whether I can further make a better choice of coordinates. Okay, I went from R1 and R2 to capital R and small r, which was center of mass and the separation between the two particles, which immediately gave me a cyclic coordinate, and I could get rid of that coordinate from my Lagrangian. I would like to ask whether there is still something I can do about the coordinates. Can I choose a nice coordinate? And you can see why I might be thinking about this, because you have here only the magnitude of that vector r. Okay, so I can do more. So this is what we will look at next.